Yeah. Good evening, class. And as you know, this is an extra session of assignment solution part. course Electronic Theory of Solids. So in this assignment, what I will be focusing on, the assignment which we have solved already. I'll be going through them and we'll be taking questions out of them. The solution is already there, as you can see. This is something which we have discussed in the class throughout our journey of this class. And I'll be just going through it, and I will be describing the key concept so that you get a revision of it. And meanwhile, if you have any doubt in any of the question, please do ask so that can be clarified like today only, or later also you can write to me. I'll be available. So having said that, let me start from the very first question, which is these are the typical question which shows up and asks for this effective mass. So the question, if you see, is which of the following is the effective mass if an energy wave vector relationship is given. So when energy wave vector relationship is given, then there are two ways you can extract it. First is you write it in terms of p square by 2m, right? The easy way will be, for free particle we have it h square k square by 2m. So you write it in that term, and whatever prefactor comes, and that will be your m star. So you write it as p square by 2m is equals to whatever is given. H bar k is p square by 3m, and that gives you m star equal to 3m by 2. That's one way. Whereas the more accurate way, if the dispersion is like cubic, let's say instead of k square it's cubic, or linear like graphene, then you will have to use the proper formalism to derive the effective mass. As you know, effective mass is when electron moves in a periodic lattice. It accounts for that periodic potential, right? So m star is nothing but, in mathematical form, if you write h bar square and the double derivative of energy with respect to wave vector k and inverse of it. Right? If you do so, you get 3m by 2, which matches exactly with like the one which you calculated. But this is only the case when it is in the terms of k square, right? If it would have been k cube, then this method will not work, right? This is just for the intuition. This is the formula which will always govern you to derive the effective mass. If we move on to the second question was like, if you are in a 1D lattice, like 1D periodic potential, then width is given, wave vector is given, energy is asked, first excited state. So energy is n square pi square h bar square by 2 m square. You put n is equals to 1 for the ground state, n is equals to 2 for the first excited state, right? And that gives you 2 pi square h square by ma square. Where h bar is Planck constant by 2 pi, and Planck constant, you all know this value. These are the standard values which you should remember, is 6.6267 per minus 20 minus 34 joule second. Right? So this is about the states. If I write it, energy versus if I write the states, number of states, so n is equals to 1 will be ground state, which will be pi square h bar square by 2 m square. The second will be, of course, 2 pi square h bar square by m square, and the third will be 3 square pi square h bar square by 2 m square, and 3 square will be 9. So that's how you calculate the energy states. And then the next question which we had was, graphite is a good conductor of electricity due to the presence of what? So as we all know that graphite is made up of this 2D layer basically of the graphene stacked on top of each other, right? Hexagonal shape basically. And this carbon has 4 valence. 3 are bonded, 1 valence electron is free. And that free electron conducts the electricity in graphene, right? And since this graphite is also made up of these sheets of the graphene, so this free valence electron contributes to the conduction. Right? So this is about it, and the graphene dispersion, as we will discuss later, it will be linear. And this is about it, about the graphite conductivity. Now we can move on to develop the theory more around the group velocity basically. So if your energy versus wave vector relation, it means E versus K is given, then simply you just have to do this thing, 1 by h bar del E by del K. Just take the derivative of energy with respect to K and divide it by 1 by this h bar, multiply it with 1 by h bar. You will get the group velocity. It is the velocity at which your average wave packet travels, right? So a, a wave packet can be made up of the many individual waves, and the effective velocity at which this wave packet travels is the group velocity. So this del E by del K you have, and then you just divide it by h bar, you get group velocity to be AA2 by sine Ka. This is particularly for this expression, but if you have any cos square Ka by 2, just simply use this form of relation of group velocity and energy versus K. If we move on to the next question, which is question number 5, and which says that assuming that the conduction electron in copper behaves as classical gas, okay, so you treat them as a classical gas, so whatever statistical mechanics you use, it should be based on the classical mechanics, right? And then calculate the average value of the electron speed. As we all know, V average is under root 8 kT by pi m, right? In classical mechanics. Yeah. So we just substitute all these values here. K is Boltzmann constant, 1.38 10 power minus 23 joule per Kelvin. T is temperature, pi is constant, 22 by 7. Me is the mass of the electron, right? You substitute all these values, and for copper, uh, since copper is a metal, you treat and the electron to be the free particle and its effective mass to be the same as Me, and you get an average speed at which electron moves in a metal to be 1.08 in 10 power 5 meter per second. This is the average speed at room temperature, roughly. So electrons just keep moving. Even if you don't apply any voltage, they will be just keep moving because of this thermal energy. And the speed at which they move is 1.08 in 10 power 5 meter per second. Now, the another type of question which can come in your exam also is like, if you, let's say if you have a type of semiconductor, to get an n type of semiconductor from silicon, it should be doped with a substance with a number of valence electron equals to. For example, this is silicon and this has these 4 valency which are bonded like this, right? Now if you want to make it n type, it means you want one free electron, right? That will make it n type. And if you want to make it p type, you remove one electron, one bond basically. So to make it valence type, you dope it with something which has more valency of electrons, and that is n is equals to 5, right? Out of these options. To make p type, you can dope it with 3, 1, 2. Well, everything is fine. But to make n type, the only solution is n equals to 5. Then this is the question based on the Lennard-Jones potential, right? So it is the potential which governs the interaction between the your molecules basically. So and it is the same principle on which your AFM atomic force microscopy works, right? So it has two parts. First is the attractive part. Second is the repulsive part, right? And if you draw this potential, this is how its shape will be as a function of r. And this point minima is the equilibrium point at which your attractive and the repulsive forces are, equilibrated. So net force is 0. So to extract the force, what you do is del V by del R, and you put it to be 0. That will give you the equilibrium position. That's how we do it. F is equals to minus del V by del R. We put it equal to 0, and then you can estimate the Rm. The position will be 2b by a to the power 1 by 6, right? And you can substitute this value in your potential form, and that will give you your potential at that minimum value. Basically at this point, your V minimum will be minus a square by 4b. That's what it means, and this is the equilibrium point. Now if we move on to question number 8, that the percentage of empty space in a body centered cubic arrangement is. So basically you extract the packing efficiency and you subtract the packing efficiency out of 1 and multiply it with 100, you will get the empty space basically. So this is easy. We do it in like I think in 11th class, 11th grade or 12th grade. So you in the BCC, this is like BCC, right? So body centered. So 1 R 1 So this r plus 2r plus r will be equals to root 3a, right? This is a, this is a, this will be, okay, this is a, this is a, this will be root 2a, and then this will be this root 2a, and this will be basically, if this is root 2a, this is a, yeah, so this will be root 3a. That's what it means. 4r is equals to root 3a, and since you multiplied with the coordination number, 8 are there which are shared by nearby 8 atoms. So you divide it by 1 by 8, and then there is a center one which is completely inside. So coordination number, effective number of atoms is basically 2, and then space occupied by atoms will be 2 times 4 by 3 pi r cube. You substitute the values in terms of a. Volume of cube is a cube. You divide packing efficiency is space occupied by atom divided by space available. So you extract it to be 68%. Now percentage of empty space will be whatever is occupied, you just subtract it out of 100, right? And that's what you get, 100 minus 68 to be 32. Now, what is the coordination number of a square closed packed structure in 2 dimensions? So coordination number is nothing but the nearest neighbor, right? It's the number of the nearest neighbors surrounding an atom or entry. So in square closed packed structure, as you can see, if it is a square closed packed structure, 1, 2, 3, 4, 4 will be there, right? So the 4 is the answer. And then which of the following statement is not true? Paramagnetic substances are weakly attracted by magnetic field. This is true, right? Because paramagnetic are the one in which if you keep them in the magnetic field, their spin polarizes, and then because of that the magnetization do appear. So they are attracted by magnetic field. Ferromagnetic substance cannot be magnetized permanently. False. Ferromagnetic are the one which can be magnetized permanently. That's why they are ferromagnetic name comes from. The domain in antiferromagnetic substance are oppositely oriented with respect to each other. So in an antiferromagnet, if one spin is up, another will be down, then up, then down, up, down. So net magnetic moment will be 0. So this is true. Pairing of electron cancels their magnetic momentum in the diamagnetic substance. This is correct, as we saw our chemistry class also, right? If it is completely, let's say, if it's completely paired, then we say, okay, everything is paired, we don't have an unpaired electron. No unpaired electron means it's a diamagnetic. That's how we do it, right? Because opposite spin will cancel each other. That's why the diamagnetism comes from. This is also true. So this is about assignment number 1, which I went very quickly. It's because this is something which you have already discussed in the class. So if you have any doubt till this point, please do ask in the comment section or through the mic also you can ask. Please ask the doubts. Yeah, if there is no doubt, then it's well and good. I mean, then we are doing exceptionally good. Okay, if it is so, then we'll move on to the next part, which is like the class 2, basically. So, if the Fermi energy of a silver is 5.52 eV, okay, if the Fermi energy is given, let's say EF, then the and the resistivity at room temperature is also given, then the corresponding velocity of the conduction electron and average time between collision. Okay, so average time between collision is tau, right? Relaxation time, and the corresponding velocity of the conduction electron. It's the basically the velocity you have to extract. So Fermi energy is given EF. If we put it equal to half mv square, we can extract the V, which is the velocity of the conduction electron, to be 1.39 into 10 power 6 meter per second. Additionally, if the question asks what is the average time between collisions, then sigma is equals to n e square tau by m, right? So we take inverse of it. 1 by rho is equals to n e square tau by m, and tau we can back calculate m by rho n e square. Resistivity is given. Mass we know 9.1 into 10 power minus 31 kg for free electron. Right? Carrier density is uh, since it's silver, okay, so carrier density we can back calculate. So EF is given. EF is actually h bar square by 2n, 3 pi square n to the power 2 by 3. EF is given, h bar we know, m we know, pi is constant, n can be back calculated. That's what we did here. So knowing the n, we substitute the value of n here. Rho is given in the question. We expect the relaxation time to be of the order of 3.7 in 10 power minus 14 seconds. This is important. You should know that the relaxation time are of the order of 10 power minus 14 seconds. And 1 femto is 10 power minus 15 seconds. So, if you want to see the process which happens at this scale, let's say 10 power minus 14, you need lasers kind of thing, which like if you want to map it with the laser spectroscopy. So, femtosecond to attosecond lasers. Atto 10 power minus 18. And for the discovery of this attosecond, recently Nobel Prize was awarded in physics, right? You all know. So this is about it. Now this is how the current flow actually. So you have higher potential. So when you have this one channel, another channel, you apply a bias EV, let's say V voltage you apply. So this goes up. So think it like the state flows like this. Yeah. So this is how the channel flows till this point, and that's why that's the reason the bottom filled band don't conduct. Only the this difference only the system wants to equilibrate, and that's why these electrons flow. Next question is, if the average time between collision in copper is given, tau is given, thermal conductivity at 300 Kelvin is asked. Okay. So, and Weidmann-French constant is given. So, Weidmann-French law tells us that K, thermal conductivity by electrical conductivity and temperature T is equals to constant. And that constant is Weidmann-French constant, basically CWF. So, given the tau, basically sigma is what? N E square tau by M, right? And K by sigma T, we want to extract sigma. So sigma, instead of we replace, to be N E square tau by M. Tau is given, M we know 9.1 10 power minus 31 kg, right? Tau is given, E square is given, right? Everything is given. So we just substitute the values, and we substitute the values. This is copper, and the above question was also, I think, okay, this was silver. So for copper, we take the carrier density to be, because we need the carrier density, right? And for copper. So this is not given in the question, but this has to be, otherwise this question is incomplete. 10 power 28 per meter cube. This need to be there. We substitute these values, and we get our K, thermal conductivity, to be 380 watt meter inverse Kelvin to the power minus 2. This is how typically the numerical question will come, right? Then the next question is the density of state as a function of electron in metal is given, right? Square root of E, if it is given, then it means it's a 3D system, right? For 2D it will be e to the power minus half. For 1D it is for 1D it will be e to the power minus half. For 2D it is e to the power 0, that is constant, and for 3D it will be e to the power half. The Fermi level at a temperature few degrees above absolute for copper, which has this electron per cubic meter. Okay, density is given, right? And carrier density is also given. Density of state and carrier density is given. Density of state is nothing but del n by del E. So if you integrate, you get n is equals to this number, and you can just back calculate the EF, which is essentially 3 pi square n to the power whatever we are doing, exactly the same thing, right? And then we get your EF Fermi energy. Basically, if you know your carrier density n and you know density of state, if n and density of state are known, then EF Fermi energy can be calculated. So any two are known, third value can be calculated, and the relation is governed by this equation. density of state is equals to del n, which is carrier del n by del E. So number of carriers present at energy E, and you take derivative of them. That will be del n by del E, and that will give you density of state at that point. That's what it means, physical meaning. Okay. The next question is derive a relation between, basically, for 2D system, a relation between carrier density and wave vector k, right? That's what it means. So we can just, your total number of states will be g times, g will be degeneracy d2k by 2 pi by lx. That's the elemental, area. 2 pi by ly will be in the y direction, and we just take out the extra part, and d2k, this region we can divide it into circle of circumference 2 pi r, right? And its width to be, this width to be dk, so it will be 2 pi k dk, integration over 0 to kf, right? And if you do so, so n by a is 1 by 2 pi k square by 2 0 to kf, and that's where we get a relation as n is equals to k square by 4 pi. And the question asked the same thing. So it's k square by 2 pi option, because we didn't account the degeneracy of 2 for spin of the system, right? If we account for the degeneracy g equals to 2, which is one spin up, one spin down, total degeneracy 2, we get the answer as given in the option, k square by 2 pi. But again, this is like for, this has, the result has to be general, right? So the general result is n is equals to g times k square by 4 pi. Like for example, for graphene, g is equals to 4. In that case, here n is k square by pi only. This is for g equal to 2. For g equal to 4, it will be k square by pi. So this is about the density of states. And the next question is, for a free electron gas in a two-dimensional system, the density of state is given as, okay, again the same thing, n versus k, we extracted now only g times k square by 4 pi in the previous question. And we know that density of state is nothing but del n by del E, right? And E is h bar square k square by 2m. Right? We just substitute all the everything here and get n in terms of E. So n in terms of E will be E times 2m by h bar square into 4 pi. And if you take the derivative, your density of state turns out to be independent of your energy, right?
Hello,
G, yeah, I can hear you.
what is
Hello, hello. There was someone, I think Chandragupta Maurya. He was saying something. Hello, this is, that is bad. What is bad? I don't get you. The voice is bad, or is it breaking? Sorry, I didn't get your point.
Sorry, sir, I forgot to mute my mic.
I see, I see, I see. Okay, yeah. So it, for the 2D system, if you see, the density of state is independent of the energy. That's what it essentially means. So m by pi h bar square. If it is degeneracy of 2, which is degeneracy of 2 means two, one spin up, one spin down. Right? So this is, so that's why the option A gets correct, that it's independent of the energy, and it's a constant which is m by pi h bar square. Now for if electron test in one dimensional, as we discussed, it goes as e to the power minus half, but all the response has since the same e to the power minus half. Then we'll have to extract the prefactor, right? Then the prefactor will determine which one of them is correct. So to do so, number of states we all know, if it is n, then 2 spin, 2 value is, that's 2, integrate over 0 to kf dk by 2 pi by lx, that's the elemental area basically, and dk basically the length which is here, which you, that you can write to be the kf, and that's what it is. So n by Lx will be your carrier density small n equals to 2 times kf by 2 pi, and since E is equals to h bar square k square by 2m, your n will be under root 2 m E by pi h bar. And since n versus E relation is given, if n versus E relation is given, then just take derivative of del n by del E, and that will give you density of state, GE. That's what we do here, del n by del E, and that gives us the relation to be 1 by pi h bar under root m by 2 epsilon, 2 energy E, this is Fermi energy E. So if I draw for 1D, it will be like this, density of state. For 2D, it is constant. This is 2D, this is 1D. For 3D, it will be like this. This will be root E, density of state versus E for 3D systems. That's what makes them different. So here it goes like e to the power minus half, and yeah, then so on. And now the next question is the conduction electron density in copper wire is given. It's 1 kilometer long. Resistivity of copper at room temperature is also given. If you connect it with the two terminal, basically with the terminals between these 2 points, what time it will take for the charge which is here, present here, to move from here to here. So I think it like if it's a 1 kilometer long wire and you are applying a voltage, how long will the electron take to go from here to here? We turn on the switch, light lights up instantaneously, but that's not something that this electron has moved. The electron which was here, that moved, and because of that only the conduction happens, because of the, and that happens at the speed of light. But the question is asking, how long will this electron which is present at this edge will take to go to the other edge? That's what the question is interested in. So we take Vd, which is E tau by m speed, because distance we know by our basic Newtonian mechanics, speed is equals to distance upon time. So if we know the speed, which is Vd, and we know the distance, so the time can be calculated by distance by speed, right? That's what the idea is. So Vd is E tau by m. Resistivity is given. We just manipulate the equation, and we get Vd is equals to E by n E tau, right? And once you know the Vd, yeah, once you know the Vd, the time taken will be the distance, which is 1 kilometer 1000 meter, divided by 2.34 into 10 power minus 5 meter per second, and that will give you around 494 days it will take. So if you have like a 1 kilometer long copper wire, you apply a voltage of 6 volt, right, between these two. So in 1 kilometer wire, this electron from point A to point B, it will take around 494 days, which is more than a year, right? It's around 1.5 year, roughly 1.3 or 1.5 years of time. So, but when you turn on the light to your home comes from maybe the nearby station, electric grid. It lights up instantaneously because that requires just the electric field to move the electron. So whatever electron was here, if that travels to your bulb will light up, right? It don't need this electron to be here. Any electron which reaches and moves will generate a current and potential, and that's enough to light your bulb. And that happens instantaneously because light, this electric field travels at, it's an EM wave, electromagnetic wave, and that travels at a speed of light, 3 into 10 power 8 meter per second. Yeah, this is about it. The next question is the density of copper is given, atomic weight is given. Well, calculate the Fermi energy. It's the same one, the one which we calculated. The relation basically, mm, you use this relation which we derived above, right? EF versus this, and you just replace with the Avogadro number, molar mass, and you calculate the carrier density. You replace your carrier density here, and that will give you your Fermi energy EF. Similarly, the electron density of copper is given. The plasma frequency. Plasma frequency is under root n e square by m epsilon naught. It is the frequency at which it will oscillate. Your electron gas will oscillate, right? And if you substitute the values which are given, density of copper, which is n, electronic charge you know, electronic mass you know, epsilon naught you know, that's the vacuum basically, permeability 8.85 into 10 power minus 12, right? If you substitute all these values, you will get your frequency to be 0.26 into 10 power 16 hertz. Yeah. So this is about the assignment second. If you have any question or doubt, okay, I think one more question is there. So the drift velocity of an electron subjected to an electric field for relaxation time. Okay, tau is given, electric field is given. We know drift velocity is E tau by m from Drude theory. This is from the class notes, and this is a standard result. I think you know. You just replace the tau E electronic charge, you know, 1.6 10 power minus 19, and m, you know, 9.1 10 power minus 31 kg. If you do so, you get Vd speed to be 3.56 centimeter per second. Yeah, I think these are the additional questions. Yeah. So till this point, if you have any doubt or question, please do ask. We have covered the Drude theory until the point, and we have covered the particle in 1D box, their energy equations, all these things we have covered. So till this point, if you have any question or doubt, please do ask. Yeah. So if there is no more question, then I'll just carry forward with the class third, which we discussed was Fermi energy and the Fermi temperature. So given for a carrier density n, we know the relation between the Fermi energy and carrier density, right? Everything else, h bar, me, 3 pi square, 2, everything is constant. We just replace all these things, information, we get the Fermi energy to be 5.498 eV. And if you want Fermi temperature, you put it equals to kBT. Where kB is your Boltzmann constant, 1.38 into 10 power minus 23 joule second, joule per second, and T is your temperature. If you do so, you get your temperature to be around 6.4 into 10 power 4 Kelvin. So that's enormously large for the given Fermi energy of 5.5 eV. That's why whatever effect you see study, they are the quantum mechanical effect. If you want to see the classical effect in the metals, you will have to go through the temperature of 6.4 into 10 power 4 Kelvin. Then you will see the classical effect. That's why the quantum theory was needed to explain these K by sigma T, the disparity between the Weizmann-French law, all those things was quantum theory was needed. If temperature T for silver is 800 Kelvin, then find the energy at which the probability that a conduction electron state will be occupied is 90%. We know that the probability of occupation is given by this equation for fermions, which is Fe is equals to 1 by 1 plus e to the power e minus ef by kbt, right? And they are asking is that the electron will be occupied is 90%. So Fe will be 0.9. So you substitute Fe is equals to 0.9, and you just calculate it, back calculate, and what you get is E minus EF by kBT is equals to ln 1 by 9. Temperature I think is given. Temperature 800 Kelvin is given, right? And what else is given is EF. I think EF is also given. Yeah, use Fermi energy data obtained in problem 1. In problem 1, we calculated it to be 5.5 eV. So if you use 5.5 eV here, temperature here, we get E. The energy at which the states will be 90% occupied will be 5.348 eV. Yeah, this is about calculating the energy per electron and the pressure exerted given by it. So it's just a derivation. This is a standard derivation which might show up like in anywhere, not here in this exam, but anywhere. This is something which you should remember. I mean, you should know how to derive it. So this is about average energy, how to estimate the average energy, and then how much pressure do the fermionic gas exert, and this pressure is crucial in understanding these galaxy systems basically. So if you take a what we call a star which collapses, so if it collapses because of this degeneracy pressure, it won't go to absolute zero because of the electron, the fermion which will be there in the system. They will try to make the size of that balloon, think like it's a balloon, will bigger, whereas the gravity will try to shrink everything in, and there will be competition, and then it will reach a stable state. That's where the degeneracy pressure, this pressure plays a role. And this, as you can see, this degeneracy pressure also is a function of Fermi energy n and your carrier density n. If your carrier density n is large or your Fermi energy is large, your degeneracy pressure P will be large. So this is the Fermi energy of a metal is given. The average energy of electron at 0 Kelvin, basically that will be a Fermi energy, is given by average of E, the temperature at which the classical free particle will have. E is given by. So we know that in the back in this question only, we calculate this. Average of E is EF times 3 by 5 times your carrier density. So this is what it is. So we extract the average of E as 3 by 5 times your Fermi energy, 5.51, and that gives you average energy of the carriers. And for classical free particles, what it will be 3 by 2 kbt, right? So half kbt for each direction. X, y will be half kbt, z will be half kbt. So total will be 3 by 2 kbt in 3 dimensions, and that will be equals to 3.306 into 10 power minus 19. Minus 19 comes, and to 1.6 comes because of this E here, and the temperature turns out to be 2.5 into 10 power 4 Kelvin. The next question is, consider two electron gas in a box of length L in a ground state. This now two boxes are pushed together to form a bigger box, which the following is not true. So basically the energy, you remember the energy expression. Energy expression is n square pi square h bar square by 2 ml square. And if you just follow it, you make L is equals to 2. If your two boxes are combining into one, then L will be 2, your energy will change. And then that's how you answer this question. The solution is given, of course. And then this is the Hall coefficient, which is very important. So Hall coefficient is, you have this bar basically in which the electrons are flowing in this direction. You apply a magnetic field, electron will curl. Because of this curl, there will be a potential difference between this point and this point, and you apply a voltmeter between here, you will see a voltage, right? And that voltage is actually Hall voltage, and RH, which is Hall coefficient, is equals to EY, electric field in this direction, JX, current in this direction, JX, EY in this direction, B is magnetic field. That's how you calculate it. And for the given carrier density, you can just do it, and RH you can calculate easily like this. The next question is for the same problem, the electron density in metal. So electron density, as you know, N is equals to 1 by E RH, where RH is Hall coefficient, or you can write to be RXY, which is the resistance which you measure here between these 2 points. If you call it RXY, will be minus B by NE, and N will be minus B by E RXY, or you can write to be N is equals to 1 by E RH, because RH is essentially RXY by B, right? So that's how you can calculate your carrier density N. Now then the next question, similar question basically, if you have any doubt, please do ask, right? A 2D kind of sheet is there with length and width, everything is given, voltage is applied, then it asks for what is the magnetic field when this current and the Hall coefficient will be, Hall potential will be 4 microvolt. So given 4 microvolt, you are asked to, what is the magnetic field B basically. So in this equation, you are asked to calculate the B given all the parameters. That's what And they do, and it comes out to be 1.09 Tesla, which is the following is the dimension of the Lorentz number. Right, Lorentz number is nothing but the Weidmann-French law. The constant is Lorentz number, and knowing the thermal conductivity dimension, knowing the electrical conductivity dimension, and the temperature, you can extract the dimension to be this one. M square L square T to the power minus 4 C inverse K minus 1. The Fermi energy for lithium is given and the density of electron is given. The electron density for a metal with Fermi energy, this will give. So since you know E for 3D goes as n to the power 1 by 2 by 3, right? So E1 by E2 for 2 material will be n1 by n to the power 2 by 3, right? That's what you do. The electron density is asked. So n2 will be nothing but n1 to the power 2 by 3, E2 by E1, and the complete to the power 3 by 2. If you calculate it, that's what it is. N2 is equal to this 3 by 2 times your N1, and you can calculate the carrier density in another material. Right? This is very important in the sense that just knowing the Fermi energy and not knowing any other prefactors, basically effective mass, all those things, you can extract that what will be the carrier density at the another point. This is about this class. If there is any doubt, please do ask. Is there any doubt till this point? And till this point, we have covered the two-day model, right? We have covered the Hall effect. We have covered the Weidmann-French law and its numerical equations. We have covered the particle in 1D box, and we have covered the effective mass concept and how to extract the effective mass from a given question. All this and what is the magnetism also, some bit of it we have just seen. In detail we will go. And apart from this, the question is, as you know, which I just showed you, they are there for the numerical question to help to guide you basically what kind of problems will appear out of these. Till this point, if you have any question or doubt in your concept or whatever I showed you, wherever you have doubt, you can ask me in the comment section, chat box, or just can open your mic and ask the question. If questions are not there, then I'll have to move on to the next class. Class 4 content basically, which is consider a state psi, which is made up of three states: psi 1, psi 2, and psi 3. This is quantum mechanics basically problem, which is given in terms of three orthonormal eigenstates: phi 1, phi 2, phi 3. Right? These ones. So psi is a function of phi's, and they are orthonormal. Orthonormal means phi 1 will be 1, but phi 1, phi 2 will be 0. That's what it means. Of an Hamiltonian H1 such that when H operates on phi, it gives n square phi n. Right? So the expectation value of H is asked for this wave function. First, we'll have to see whether it's normalized or not. Right? So expectation value of any operator, whichever you want to calculate, is given as bra. This is known as bra. Then H operator, whatever operator you want, and then this part is known as ket. So this is known as bra. This is known as ket, and then psi. So when this Hamiltonian operates on wave vector psi, it gives n square times phi n, right? When it operates on phi n. So when it operates on 1, it gives 1 square. When it operates on 2, it gives 2 square. When it operates on 3, it gives 3 square. So now you have this state. You just multiply it with the bra part of it. And orthonormal means this. If I is equals to j, let's say phi 1, then it will be 1. But if it is phi 1 and phi 3 or phi 2, it will be 0. That's what it means, orthonormal. And if you do so, you get it's 22 by 10. And now we calculate the denominator, which is again the normalization factor. The denominator turns out to be 11 by 8 by 10. So the total will be numerator, which we calculated 22 by 10 divided by 8 by 10. This will give 11 by 4. Yeah, that's how you calculate the expectation value, right? And then 2D lattice of graphene is given. Basically, then it asks for these the beginner side cell. So beginner side cell, this will be the beginner side cell, and for this one you need B1 and B2 to calculate the area, basically. So this is just the numerical part which we did to calculate this area, and this turns out to be 3 root 3 a square by 2. It's an area of an hexagon, basically. If you calculate this, if this is a, then its area will be 3 root 3 a square by 2. So continuing with the previous problem, lattice graphene, the Bravais lattice for this array. So Bravais lattice is a rectangular lattice with with basis vector b1 and b2, basically. And Bloch theorem is about the wave function vector in a quasi-particle. It is stated as psi x plus a is this, which of the following is also an equivalent form of Bloch theorem. So what Bloch theorem says is that if you are in a periodic lattice, let's say, right, and then your psi x plus a will be just your function will remain psi x. It just acquires a phase e to the power I k a. If it satisfies this criteria, it will be Bloch theorem part. If it doesn't, then it is not a Bloch theorem, right? So that's what we try on all of the given 4 options, and what we but we find that option number 2 only satisfies this criteria. Rest option do not satisfy this criteria. It is just a numerical exercise. It is something which we have already discussed in the class earlier. It is just for the revision. Today's class is just for the revision of whatever we have had in our previous classes, just to get a glimpse, like because it's been a month old, right? Before a month only, we had these classes. So at least 6 class will cover, so that because last 6 will be fresh, I think, but the earlier 6 you might have forgotten few of the concepts. So that's why I want to focus on the earlier 6 one. When we impose boundary condition on an electron confined in a quantum well, basically only discrete values k are permitted. When we impose periodic boundary condition on a string of n atoms, how many discrete value of k are there and what is the spacing? So you treat it like the 0 to n length, total will be na, and the spacing is a. Then just you use the Bloch theorem that whatever it is here, the same wave function will be here, right? If you close a loop out of it, of this string, the wave function which is 0 at 0 will be should be same as at L, right? Because they are at the same point. And if you do so, you get k is equals to 2m pi by na. Yeah, that's what it means. And then consider 2 hydrogen atoms with 0 energy and hopping terms 1. The change in ground state energy after allowing for hopping is. So this is essentially about mm, the hopping parameter, basically. So psi1 will be as this is the ground state energy of individual atoms, and if this is the hopping energy -1, right? That's what it means. This factor is -1. If this is so, then we determine the eigenvalues. Eigenvalues of any matrix you can determine, like of H matrix you can determine H minus ES is equals to 0, right? And if you do so, you can extract your E to be which will be your eigenvalue equals to 1, E is equals to plus minus 1. So if your energy E0, you take it equal to 0, then a state will be split into +1 energy and the -1 energy. These two states will exist now. Then if you bring 2 hydrogen atoms near, and this is what we call bonding. This is of the less energy bonding orbital, and this is what we call anti-bonding orbital, which is of the higher energy. The translation operator Tx is defined as this, which of the following is false. If this is just numerical exercise, mathematics. This you can go through. I will anyway upload these class notes there, so you can just go through it, and you will see that option 4 is true for that one. And density of state of free particle in a one-dimensional solid of length L. So this you can just calculate, the one which we did for the 2D and 3D and 1D. The same thing you can do for one-dimensional solid also of length L, using the same n is equals to Lk by pi, and then just replacing the energy expression with the carrier density and all the stuff you do. It just rearrange the thing and you will get your density of state as 1 by pi del E by del K, and that gives you essentially square root of e root power minus half for 1D. This is just another form in which it is written. The another form can be e to the power minus half. This is about the just about the trace. I mean, if the two elements are if commutable, if the two operators are commutable, then what does it mean? That's what this question is all about. This is something we already discussed. So it's just the quantum mechanics concept are there. If the two commute, then they can have the common eigenfunction basically, right? All those things are there. If the two operator commutes, that's what it means. If the two operator commutes, then they can be measured independently, unlike momentum and mm, what we call position and momentum, which don't commute, which gives IH bar. If you take momentum and let's say uh, mm, any parameter px and y direction, then they will commute, they will give 0, right? And in that case it will be they can be measured independently, but px and x don't commute, then in that case you can't measure momentum and position independently and sharply correctly. So there will be an error of always IH bar. Corresponding uncertainty will be IH bar in the measurement. So this is about class 4. If you have any doubt till this point, please do ask, because this is the last class. After that, there will be no more classes. You can write to me. I can respond you through emails, but it won't be a live interaction, most likely. And if you have any doubt, then it will be with you only. Okay, doubt is not there, then we'll move on to the last class, basically the class 6. This is the class 6 and assignment number 5 and class number 6, basically. So, given delta ij is equals to 1 and 0, if I is equals to j, and if I is not equal to j, this is 0. This is delta function, right? Dirac delta function. Then this is asked about what will be the value of ABC is equals to 1 to 3. Basically, 3 of the available states are there. In that case, when A is equals to B is equals to C, for those cases it will be 1, otherwise it will be 0. And since ABC can have a value of A is equals to B is equals to C can have 1, A is equals to B equal to C can have 2, A equal to B equal to C can have 3, and for all of them it will be having 1 plus 1 plus 1, the total will be 3, so that's why the correct option is 3. For electron moving through one dimensional periodic lattice of periodicity A, which is the following corresponds to an energy eigenfunction consistent with Bloch theorem. So we know that psi x plus a for Bloch theorem is e to the power I k a psi x, right? That's what it means for the Bloch theorem. And if we just substitute all of the options, we get that only the second option satisfies this criteria. Rest fails to do so. Then the next question is, which of the following statement is not correct about the Brillouin zone of a square lattice? The first Brillouin zone is a square of side 2 pi by a, right? So this is correct, right? The first Brillouin zone is this one. Okay, this is the first Brillouin zone. So this is 2 pi by a and this is 2 pi by y. Okay? So this is correct. Option A. There is the first Brillouin zone and the area of the any Brillouin zone, first, second, third, fourth, fifth. Uh, all the Brillouin zones have the same area. That's the basic concept. The first option is correct, second is correct. The k points are equidistant in kx as well as in the ky direction. Correct? This is true if the lattice is square. If it is rectangular, then it won't be true. The area of the second Brillouin zone is twice that of the first Brillouin zone. No, all the Brillouin zone have the same area. So for example, for this one, the first bullet zone will be this one, right? The second bullet zone I think will be something like, so how you calculate the first bullet zone and second bullet zone is like this. For example, you want to calculate the first bullet zone. So your nearest neighbor you connect. This is your first bullet zone. This process is known as beginner site cell selection. This way you will get always the first bullet zone. If you want to extract the second bullet zone, you join the second nearest neighbor like this, this, and this. You make half of it, this half, this half, this half, this half, and then connect it. So it will go and connect like this, right? So first Boolean zone was like this, somewhere in between, and this area, in between area, this will be equals to the area which is inside, kind of thing. You can think it like that, and that's why all the Boolean zones have the same area. That's why the option 4 is correct or incorrect. And since the question asked about the not correct, so option 4 is the correct option for this question. This is how you can think it. The first Boolean zone is shown in the purple, second in the red, third in the green. That's how it is shown. If this is clear, then we'll move on to the next question, which of the following can never be beginner site cell for any 2D probabilities? A pentagon, of course, because uh, if square will have a square. If you take a square and you make probabilities of it, it will be square. For rectangle also, it will be a rectangle. For pentagon, it won't be pentagon. For hexagon, it will always be hexagon. So the correct option is pentagon. And then the next question is, given the energy dispersion of the form E is equals to epsilon naught minus 2t by 2t cos theta. Consider general solution of the form is also given. Then for periodic boundary condition, the theta is okay. Then it is asked what is the theta. For periodic boundary condition, what does it mean? If u1 is un plus 1, u0 is un, right? So we substitute basically whatever form is given, we substitute these values here, and we just equate it, and we get, if we just equate it, and in the periodic boundary condition, as we know that u1 u0 will be related to un plus 1 and un through this relation, right? So if we do so, we can back calculate our theta, and theta will turn out to be 2k pi by n. This is about the periodic boundary condition, which says that okay, till this point you had the state. After this, the same pattern repeats. If it repeats, then in that case, un will be equals to u0, u1 will be equals to un plus 1, and that's what it means in the equation, these two equations. That's what the physical meaning is. And after that, it's just a mathematics part, which you just can calculate easily. For a nearest neighbor tight binding model in 3 dimensions, the bandwidth is okay. This is about the tight binding model, right? So in the tight binding, we have this base energy is zero, what we call, and then the hopping energy, which is like minus 2t. If it is 1 dimensional, it will be cos kxax. If it is 2 dimensional, it will be cos kx plus cos ky ay. If it is 3 dimensional, it will be cos kxax, cos ky ay, cos kz az. That's how it will be, right? And if it is uh, 3 dimension, so we have these three. Now since t is equals to minus 1, and this can have a maximum value of 3, right? 1 plus 1 plus 1, and minimum value can have is minus 3. So minus 3 times 2, minus 2 will be plus 6, so that will be this state. Minus 2 times plus 3 will be minus 6, that is this state, which is anti-bond, which is bonding. Top one is anti-bonding, higher energy, and the bandwidth is a delta between these two, difference between these two. So difference between plus 6 and minus 6 is 12. That's what the correct option is, 12. For low energy near the Dirac point, which of the following is true about graphene? Okay, graphene has linear dispersion. That's what the key point about the graphene. Like generally electron have parabolic dispersion, right? H bar square k square by 2m. but graphene has linear dispersion, which is h bar k Vf. E is equals to h bar k Vf. The next question is the band energy of a conduction electron in a tetragonal crystal is given by. So tetragonal crystal is something where you has like something like this. So x square by a square plus y square by a square plus z square by b square, right? If something is like this, then this is known as tetragonal crystal. This kind of Fermi surface, basically. And in that case, for sphere, we need A is equals to B equals to C. So sphere is not true, right? For tetragonal, it's not possible because it will be tilted kind of thing. Basically, it will be like this. Right? It's not possible. For ellipsoidal, yeah, I mean, if you compare 1 and 2, given dispersion is ellipsoidal because uh, I mean, it's an ellipse of which it's an ellipsoidal of which this A and this B and then there will be C also if the 3D. So they are maybe these two are A and this is C, which is M1, M1 and M2. So this can fall under ellipsoidal. Since every sphere is ellipsoid, but every ellipsoid is not a sphere. So with that logic, only this option third satisfies the criteria. For toroidal, this has to be the equation, but this is not the case here, right? So that's why option 3 is correct. Then option 4 is about calculating vector a1 and a2. This is an easy job with just a geometry mathematics. You take projection of the lines and then that tells you about what will the coordinate of these points. And if you take coordinate of this point, you can do a2 minus a1 to know this wave vector b2, right? That's how you do it. Choose the correct option. Properties of graphene. Graphene has extremely high electron mobility. Correct. Graphene has lowest electrical resistivity among non-material at room temperature. I mean, theoretically at 10 power minus 16 ohm meter. Graphene is highly permeable. Yeah, correct, because I mean its shape is like this, right? And so this space inside through which any atom can move or pass, the space is very tiny. So you can say that it's highly impermeable. So all are correct. So with this one, I'll conclude this session in this class. Uh, till this point, if you have any doubt or any question, query, please do ask. And if there are no question or no doubt, then we will end the session here. All the best for your exams. Do well, get good grades, and learn the concept. And meanwhile, since it will be on 22nd or 24th, I don't know. Just prepare hard. If you have any doubt or question, just drop me a mail on Mohit on an email mohit jat@iic.ac.in. I will reply as soon as possible to help you through the doubt or clear in doubt if you have. And with this one, all the best for your exams. And I will conclude this session here. You may leave the class now. And